Okay, good morning, everyone. Thank you for joining us. Today is the final presentation in our April webinar series. My name is Adam Galata. I'm the marketing manager for the EMEA region at Monolithic Power Systems. Today I'm joined by Marco Hepp. He's our business development manager for sensors, and he will be presenting solutions for ultra-low power angle sensing. Before we get started, if you have any questions during the presentation, please type them into the question box in your Zoom control panel. These questions will be read aloud at the end of the presentation during our Q&A session, and they will stay anonymous. All of our webinars are available for on-demand streaming on monolithicpower.com. Today's webinar will be added shortly after the presentation, and I'll also send up a follow-up email with links to the presentation materials. Now let's get started with the presentation, and I'll turn it over to Marco.
Thank you, Adam, and hello and welcome everybody to this webinar, Solutions for Ultra-Low Power Angle Sensing. May I introduce myself? My name is Marco Hepp. I'm the Business Development Manager for sensors in the EMEA region for Monolithic Power Systems. I'm now more than 27 years in the semiconductor industries and more than 13 years in IC technical support, sales, and application. So you can contact me at any time over networking and by email or phone. So yeah, on our agenda today, first we should talk about the motivation for ultra-low power sensors, the possibilities with Hall-based position sensors, what are combined solutions with such ultra-low power angle sensors, how to solve power saving in systems, about the effective method on wake on change to save a lot of power, and the systematic impact of those methods and combinations. And at the end, Adam mentioned it, we will have a Q&A session on your dedicated items. So talking about motivation, today everything is, let's say, always on. It's all digital, it's in the cloud, it's connected in networking, it's automated, it's battery powered, it's secured. So there are a lot of things and a lot of applications that are growing more and more, and areas that have been, let's say, impossible to be implemented are state of the art over the last few years already. And it's a continuous growth in those applications. And this also means that sensing angles and movements and interactions is also required. So having a look at angular sensing here with a MagAlpha family from Monolithic Power Systems, we do see here possible sensor ICs on different magnetic positions to sense over a Hall effect using the SpinAxis principle with an early conversion from analog to a digital world, including digital filtering, with a variety of different digital outputs and the option for a non-volatile memory on chip. So what are the MagAlpha SpinAxis advantages? So the resolution here ranges from 8 to 14-bit, but here we have a very conservative, let's say, statement about resolution. What means resolution should be plus minus 3 sigma. That means we're not just adding some bits. This is a real representative value by 3 sigma. Then we have a very wide speed range up to 100,000 RPM, or depending on the situation, sometimes even a little bit more. We are very flexible on magnetic topologies like side shaft, end of shaft, and even side shaft orthogonal. Our sensor system with the SpinAxis principle is a very fast angle sensing system. So we do sampling within 1 microsecond and have latency of around 3 to 10 microseconds at a constant speed. Our magnetic field range is very wide. We operate typically in a range of 15 millitesla to 100 millitesla and even more. Here, this means if you are below this wide field range, the sensor will continue working, but your resolution will maybe trade off a little bit, like, for example, half a bit. Those sensors are very small. The standard package is a 3x3 QFN, and we have one part that is already in a 2x2 millimeter QFN package. But the main advantage here on SpinAxis in the MagAlpha family is that we have ultra-fast power up in our system. And this ultra-fast power up has a big benefit for low power sensors. So we will have here a look on dedicated parts for low power applications, the MA780 and MA782. The 82 is the 2mm version. This is the 3x3mm version. We go here up into a range of up to 12-bit resolution, same maximum RPM speed, same sampling, low latency, same region of magnetic field, here including fields above 100 millitesla that will cause a less effect on the resolution than on lower fields, but we are capable to sense very high fields too. The small package is mentioned. This is really for a sensor size extremely small when you have a 2x2 package for a complete sensor system. But important here on all this family is that we have for low power consumption dedicated modes and triggers and I/O pins. So having a look at the block diagram, we do see here the classic SpinAxis two-dimensional in-plane Hall sensing. We do some filtering and we do this amplitude detection, what is very important to sense if the magnet was pushed or not, for example, in an HMI application, but also to detect a loss of a magnet or some misplacement. We do here on the SpinAxis technology a phase detection. This means a time to digital conversion and a dedicated digital filter functionality, what is very important. You see here in this gray area close to the interface that we are able to be ready, always on and ready at the power consumption with less than 1 microamp. But when the bigger sensor part is active, we will really pull 10 milliamps. This sounds a lot, but it all depends on how long we do turn on all these power consuming components and when can we turn them off back again. So it's all about the timing. And here we can see the 10 milliamps in the active phase and the 1 microamp in the standby phase or the idle phase. Important here is that the ratio between active and standby is, let's say, small enough. That means we have a very short active and a pretty long standby time. We do see that here in this table. If we, for example, sense at a 5 Hertz, what is a typical HMI human-machine interface sampling rate for user interaction detection, and we are sufficient to sense this knob by an 8-bit position value, our average current is just 4 microamps. If we want more precision, that means not 8-bit but 10-bit, we will extend in the filter functionality, we will increase a little bit on time, and we will end up at 60 microamps average current for those 5 values per second. So important is that the power cycling is dealing with this active and standby states. This can be done by user control, by an automatic mode, or by a wake on change mode. A tiny feature that will become more and more relevant in the future is that the I/O voltages, especially due to very low power FPGAs and new microcontrollers, is also selectable due to their pin voltage that may be 1.8 to 3.3 voltage. The sensor will always be supplied by 3.3 voltage. And having a look at those modes, I mentioned this user control mode, and we see here the microcontroller takes control on everything. That means timing, waking up the sensor, reading the position when data is valid, and putting it back to sleep. This is something that I would say almost everybody is capable with a sensor. So it's not really a big thing. The second mode, the automatic sample cycle mode, here the timing is inside the sensor, and the sensor wakes up the microcontroller with a data valid indication, and the master accesses over the SPI interface the position data. The third and most interesting mode is the wake on change mode. Here we do have a timing inside the sensor, but we also have a decision to say, has the position changed within a dedicated range that is permitted, or did it exceed that range? And if so, only then there's a new data notification to the microcontroller. So having a look at this user control mode, the most simple mode, and we see here the details in the sensor, there is always a startup time for the sensor structure, a filter settling time as a part of the sensing, and then the access from the microcontroller to pick up the position information. After all this, the sensor is put back to sleep. Important here, we can turn off the internal sensor system, but still access the old value, even maybe at a shortly later time. That means we can really turn off the sensor and access to this value that was generated in here, even a little bit later in idle state. On the automatic sample cycle, ASC, we have a sensor-based timing, and in that case, we could, let's say, run the sensor and use the SPI to detect activity or an update. People would say this is polling, so it's not the most efficient way to operate this microcontroller, but it's possible, especially when you do not have pins left over for this data valid indication that we show here. Here we say it's automatic sample cycling, but we have a data valid indication like an interrupt request to wake up the microcontroller, and then the microcontroller will access over SPI our new position data. There's a benefit here that we can have with zero threshold. We can have always the active phase and then later on the microcontroller with the reading. What we can also indicate, there is no new position, so you do not have to access. I don't have to wake up. This is a small benefit and goes into the direction of the next mode, meaning on-demand waking up. And this is the wake on change. That means a sensor-based motion detection and decision. Here we have a sensor output. This is the angle, and due to the internal timing, it will directly sense with the configured update rate the angle and internally decide, am I in this threshold band or did I even exceed? And if the sensor detects an exceeding angle, for example, due to user interaction, it will notify by new data this new value exceeding the threshold and the former reference. That's the center base here. So the microcontroller is just woken up if the user has turned the knob. And most of the time, the user or the microcontroller is sleeping. Here, a nice feature that the MA782 provides is a following reference. That means with every update, the latest exceeding reference is put into the new reference. That means you do not have to update the reference by the microcontroller because the sensor already has this value. This is another feature to save even fast SPI communication, save some time. Okay, we have heard about all those modes. So what is it all about? Where is the impact on those modes? So we chose a popular HMI, human machine interface, a popular knob condition situation. And in that case here, we said, okay, we make 5 Hertz, that's 200 milliseconds update rate. Our sensor will pull in the active state 10 milliamps, but the active state is just 35 plus 1 microsecond. And in that case, in the idle phase, we're just with 1 microamps, very low on power consumption. For the microcontroller, we chose here an ESP32, a very popular Bluetooth LE Wi-Fi radio. It's a super equipped microcontroller, very impressive. And you can really choose the demand of power depending on your infrastructure. It goes from up to 700 milliamps, enabling everything at the highest power rate to a reasonable, we considered here a Bluetooth low energy rate of 35 milliamps. But this, including the access, we estimated for a user control mode 70 microseconds, for ASC mode 25 microseconds, and same with the wake on change mode. And in sleep state, this ESP32 will drop down to 10 microamps. So if we compare this here and say the user control mode is our 100% reference, how much current or power can we save here? And we see that it really drops dramatically by the mode, and ASC and wake on change are not really the difference, except the user interaction. That means how often is the knob rotated or moved beyond our threshold of the reference. And when we say, okay, we move the knob every second, what could be, I would say, something like a mouse wheel with a very, very active user, then we already just consume 58%. So this is already a nice drop. And 10 seconds is already going down to 55%. But we can see here there is an asymptotic limit that we do not exceed. And this is caused by the sleep consumption and by the sensor update rate and the sensor consumption. So even if we would turn our door lock just every 4 hours, we end up at 54% compared to a classic operation mode on power demand. One thing about mixing modes is not everybody is too happy with a CMOS-based timer, and sometimes, especially in Wi-Fi integrations, you have the situation that externally Wi-Fi communication is also demanding position information. A good example here is the door lock. If you have a remote wireless activation of the door lock, the sensor needs to sense the motion that is controlled by the motor and the master. And in that case, you need more and more often sensing this in parallel to the ASC mode. So in that case, you can really mix modes and access the device on demand or on sensor timing base. We see here some ultra-low power applications, very popular applications. We see door locks, we see thermostats, we see user interfaces on the computer. And this is just a small picture on the possibilities. So there's a big variety of many applications, many application ranges. Important is typically low power or battery powered devices, interactions, and sometimes it's a combination, especially in the door lock, and here also in the thermostat at the heating, that you have to combine a motorized axis and a user axis on the same sensor. So this is also possible. Talking about resolution and filter functionality, this is a very special feature inside the low power devices. It's by principle a part of the SpinAxis technology that we use. We have a very flexible and very wide configurable filter window. And this causes very fast access, means very short filtering time, and also very deep filtering with a very long time. So this would be 65 milliseconds, what is a huge value. But the thing is, not every application is happy with a low bit rate. Some applications also want a 12-bit value, a very precise position. And in that case, you can extend up the filter value regarding to the ability to gain more bits, and also to run in really low fields. This is a combination of weak field and high bit quantity. And this feature, that means that we can very flexibly configure our filter. We are not just limited to turning knob speeds with our low power sensor. So this is not the only application. With those low power devices, you can go into a full rotary encoder application with no problems. Due to the configurable bandwidth, you can go up in the speed up to 100,000 RPM and also 12-bit of resolution. So this is definitely not an HMI speed, and some HMIs run in a 10-bit world, but 12-bit is typically a classic encoder or motor application. Motor applications, the same situation. Typically, you would expect a UVW commutation indication due to a fast angular sensing. With the low power devices, you can sense the angle, but you do not get UVW signals. You also, in the encoder world, do not get ABZ output signals or even PWM. And this is a trade-off when using this low power sensor, it's not that it's not capable for high resolution and high speeds. It's just that those classic real-time demanding interfaces do not really make sense in low power devices. And also, due to the situation that we needed some pins to communicate this interrupt and requesting notification, there were just not enough pins to provide this. So using this sensor, even in high performance applications, is definitely possible, but it's typically requiring an embedded system structure here. So putting a line under all this, enabling ultra-low power system architecture, what is very important is that the ultra-low power capable sensor needs to have a wide configuration range because the applications are very, very different. The operational range is also important, that it's not just limited to very slow or very simple low resolution applications. So overall, including the performance of the internal sensor core system and filter structure, this requires a high performance or wide performance range to enable this low power. With these fast sensor systems, we keep the on time short and the idle time relatively long. So at the end, we would say that the system structure flexibility, that means how to combine the controller and how to combine different modes at different stages of the application phases. This is very important. And here we see that the roles of master and slave may vary. Sometimes on timing, the sensor is the master. Sometimes the microcontroller is the master. The microcontroller will be always the SPI master, but on timing and interaction, it can be that the sensor will take over and decide, for example, with wake on change, when to wake up the microcontroller or if not. And this brings a very big power saving benefit. So we do have not just a time-based operation, we also have an event-based operation. And when you consider the door lock as a very seldomly used door, for example, on a household with 4 persons, there will be, let's say, 20 to 30 door interactions over a full 24 hours. And this really saves a lot. Mentioning here, our MA782 is the smallest, world's smallest absolute IC encoder. And with this sensor technology inside this package, we can go into very, very small, ultra low power applications. For the summary, we see that there's a huge growing low power application range. A lot of things get automated, sensed, whatever. With Hall-based position sensor systems, you can sense this low power application, even when people say Hall requires current to sense an angular position magnetically. When it's possible to run that in a very fast time, it's possible, and there are available ultra-low power angular sensing solutions that are Hall-based. So it's all about saving power very effectively, and this is all about timing, waking up, interrupt, signaling, etc. And with combining multiple modes for user interaction and motion control, we're not just limited to the knob-based slow speed and low resolution applications. We can even increase to classic motion control and classic encoder application. So at the end, the system structure and the design of your low power system is important, and the sensor needs to be as flexible as possible to save as much power as possible here. Okay, I would say that's it for now. Are there any questions?
Thank you, Marco. We'll take a look here and see if there's any questions. I think right now everyone has enjoyed this wonderful presentation. We'll just ask one more time. If you guys want to ask a question, please use the Q&A box at the bottom. And we'll just wait for a second here and see if anybody has anything. All right. Thank you, everyone. We appreciate you guys being here. If you have any other further questions regarding today's topic, please feel free to email me. My contact information is located in the invitation. You can also contact Marco Hepp directly. His contact information will be included in the presentation that we send out as a follow-up after this webinar. So we've got a few other ones. Some people have piped in with some questions. Okay.
So what does the resolution mean in sigma? The thing here is that, and let's scroll a little bit back in the slides, 1 second. Good question, yeah. Talking about a resolution means you always have a signal and you always have a part like a noise. And in that case, the resolution here is really the quantity of bits that are stable with a plus minus 3 sigma. That means you get, even with the least significant bit, a plus minus 3 sigma precise position information at that bit level. So it's not just like extending the bits and showing on those bits a high noise part. This 3 sigma is something like, I think, 98 or 99% of the real position value. That means it's from the statistical Gauss curve, very precise and very close regarding the resolution. And that's what we state here with the resolution. Typically, the output bits is more than just the stated resolution. So you would see more noise, but the resolution that is confirmed in the bit length is the most relevant part here. And we consider this as a sufficient, but also mandatory barrier between real signal and starting to become noise. Yeah. How many Hall sensors are inside the angular sensor? Ooh, that's a good question. Actually, I do not know all those technical design details inside the design. I would have to check with the team about this detail on the SpinAxis circle. It is a set, but I'm not sure how much it is actually. I'm sorry, but we can check for that and go back to you later on. Yeah. Also a question regarding the supply voltage of 3.3 volts. Right now, all our sensors are from the core sensor voltage. 1 second. From the core sensor voltage are 3.3 volt based, and we permit an I/O voltage of 1.8 to 3.3 volt. So the core sensor, the internal oscillators, the SpinAxis system, the filters, they will need 3.3 volt. We do not have a full core sensor technology that is already able to be supplied with 1.8 volt, but we will pick this as a feedback up. And we know there are applications, ultra low power applications, that are really looking like the FPGAs for a very low core voltage. Here, the core voltage is on all parts, all position parts, 3.3 volt. Yeah, non-volatile memory, very good question. The non-volatile memory here inside this structure is not a OTP device that you can program just once, or let's say with an option twice or 3 times. We do have here, by the foundry and by the technology, a guaranteed possibility to program this 1,000 times. Typically, the non-volatile memory is just containing some filter features and the zero positioning. And I would consider this as not really a configuration, just a configuration, not a calibration. So there is no dedicated calibration required for those devices. There is no offset, no ratio, no phase shift, no nothing here. The sensor themselves are calibrated in factory, and due to the principle, they are really very robust on this. So the user just needs to configure the zero, typically in factory, for example, when the knob has a bar, and some filter features, the filter length or the depth of the filter, to enable the maximum RPM speed and provide the maximum on precision information. Oh, a very good question. Could you be more specific about the resolution for very small magnetic fields, smaller than 5 millitesla? What about the noise in that cases? Oh, that's really a very low field, 5 millitesla. And when checking here, our recommended field minimum to get those 12 bits is 15 millitesla. Actually, you can simulate the resolution that we expect on our website in the magnetic simulation tool, and then you just define a magnetic setup with a field of 5 millitesla, and it will give you the result on the bit resolution. So this is a possibility here. On our MPS website, we do have in the sensors, in the position sensor section, a link to a dedicated free-to-use magnetic simulation. We will follow up on that, and I will set up a configuration with a very distant magnet and a very small and not strong magnet to get those 5 milliteslas. The sensor will work, but the noise will eat off some of those resolution bits. Actually, I'm not really sure where we will end up, but the line typically drops almost linearly to the field, and in that case, it could be that you are in a 9-bit range, but we need to simulate that. And you can also simulate that by yourself because the tool is very easy to use. Okay, I think that were all the questions.
Yeah, looks like that was it. Thanks for coming in with those questions here at the end. Again, if you have any further questions, you can email myself or Marco. We're always planning educational and solution-based, product-based webinars. So check back at our website, monolithicpower.com.